Hello and welcome to today's IWCS webinar. Now, I'm pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference session or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today we welcome Dr. Earl Parsons, Principal Optical Engineer, CommScope in Texas, USA, who will be presenting his paper on angled 16-fiber MPO connectors for 400G-SR8 applications. Dr. Earl Parsons received a BS in Electrical Engineering from Brigham Young University in Provo, Utah, USA in 2006. And an MS and PhD in Optical Sciences from the University of Arizona in Tucson, Arizona, USA, in 2008 and 2010. From 2010 to 2013, he was a senior member of technical staff at TE Subcom, formerly known as Tyco Communications. Since 2014, he has worked as a principal optical engineer at CommScope in Richardson, Texas, USA. His current interests are multimode and single-mode fiber optic systems. Dr. Parsons was a recipient of the IEEE Dallas Photonic Society Volunteer of the Year Award in 2017. Earl, we welcome you to present at today's IWCS webinar series event.
Great. Thank you for that introduction, and thank you to everyone for joining today. Hope that you and yours are staying healthy and safe during this time. Today I'm going to discuss angled 16-fiber MPO connectors for 400G-SR8 applications. And before I begin, I'd like to recognize and thank my colleagues at CommScope who are listed here on the slide. Thank them for their diligent work and their contributions to this effort. So in IEEE 802.3, the 802.3 CM Task Force recently completed a standard, and part of that standard included specifications for 400G SR8 transmission. Now, this application uses 8 multimode fiber pairs, the OM3, OM4, or OM5. So with 8 fiber pairs, there's 16 fibers in total, 8 to transmit, 8 to receive. And each fiber carries a 50 gigabit per second PAM4 signal centered around a wavelength of 850 nanometers. With PAM4, we have 4 levels of optical power to represent the digital data. With NRZ, on-off keying, which is our traditional data center modulation format, there are just 2 levels. You could have a high level of power to represent a binary 1 or a low level to represent a binary 0, for example. But with PAM4, there are 4 levels, and since we have 4 levels, each level can represent 2 bits of information. This allows us to double the data rate while keeping the baud rate the same. The challenge with PAM4, since there are 4 levels in the same space that there used to be 2, each level is closer together, and so this modulation format is more sensitive to intensity noise than our traditional NRZ on-off keying modulation. The standard, written by .3CM, allows for an MDI interface, the transceiver to cable interface, to have an MPO connector with 1 row of 16 fibers or 2 rows of 12 fibers. And we're seeing more popularity in the market with 1 row of 16. And in fact, we're finding in the wild transceivers packaged with an angled 16-fiber MPO interface on the front of that transceiver. And the reason we are seeing these angled multimode connectors is due to the end user demand. These angled multimode connectors have not been standardized yet, but the end users are requesting them. For example, you can go to the study group of IEEE 802 that led to the .3CM task force, and you can find some presentations made by a person employed and affiliated with Google where they publicly proposed a 16-fiber MPO that had an angle, in fact, the same 8-degree angle that we see with single-mode connectors. Since these connectors are new to the marketplace and to the industry, my colleagues and I decided to investigate them. We wanted to look at not only the return loss of these angled multimode connectors, but also see if they impact the system performance. And what we found is that PC connectors, or your regular flat multimode connectors that don't have an angle, they can support SR8 transmission with no penalty if the connectors are clean and if they're well polished so that they have an end-face geometry that's compliant with standards. On the other hand, if you have PC connectors that have low return loss, which is poor return loss, due to an air gap or a small gap between the fibers, well, that air gap can degrade the actual system performance, not just the return loss specs, but the actual BER. And finally, we show that using APC connectors reduces the risk of poor performance by offering high return loss, even if you have an air gap between your fibers. To investigate the angled multimode connectors, we realized that it wouldn't be as simple as angled single-mode connectors, the main difference being the fact that multimode fibers have a graded index core. So that means that the index refraction of the core varies with radial position. The center of the core, you have a high index of refraction, and as you move towards that core cladding interface, the index refraction drops off until you get to the cladding index, which is lower. And the acceptance angle of a fiber, or its numerical aperture, or NA, depends on the index of refraction between the core and the cladding. So we can see in this equation, NA as a function of the acceptance angle, which in turn is a function of the refractive index. And so the bottom equation shows that the NA is a function of radial position. On the bottom right, I have an image that shows that the acceptance angles for different parts of the core. Of course, in the center, we have a larger NA, or a larger acceptance angle, and those decrease as you get towards the edge of the core. So we need to keep these things in mind when we're figuring out what's the benefit or what's the impact of having an angle on that fiber end face. So we simulated using several different tools, the reflected light when you have an angle for different angle functions. So just like with single mode, the intention here is by introducing an angle is when you have light hitting a interface at the end of the fiber, that angle causes the reflected light, or a portion of the reflected light, to be directed outside of the core. So it doesn't counterpropagate down the fiber back to the transmitter and cause problems there. And we found that even with multimode fibers with their gradient index core, the angle does improve the return loss. It does reflect that light outside of the core. On the top right, we have a chart that shows the improvement in return loss as a function of end face angle in degrees. And we see that as that end face angle approaches 8 degrees, the return loss improves dramatically. So that angle should improve the return loss by up to 30 dB or more. On the bottom right, we have results from a ray tracing program. These are the reflected rays for different end face angles. So if we have 0 degree, then many rays are reflected back down the fiber and counterpropagate. And as we increase that angle, we have fewer and fewer rays that are coupled into the fiber upon reflection. To verify these results experimentally, we manufactured a series of connectors with flat ferrules and angled ferrules. And we found that the APC connectors have higher return loss values, which is better return loss than your UPC or your flat connectors, even when those angled connectors are unmated. So in the top left chart, we have results from some 16-fiber UPC connectors that were manufactured in our lab. Now this is just a flat connector, what we typically see with multimode. And we have return loss plotted versus the fiber number 1 through 16. And we see that these results, all the fibers have return loss between 30 and 40 dB, and the results are fairly flat. The fibers in the middle of the ferrule and the fibers on the edges of the ferrule have more or less the same return loss. We then manufactured several multimode cables with angled connectors. We took pre-angled single-mode ferrules that have an 8-degree angle and populated those with multimode fibers and measured the return loss. We see the results in the top right, and the return loss values are much higher. They're higher than 45 dB up to about 70 dB, so significantly higher than what we see with the flat connectors on the left. Now, those flat connectors on the left are all above 30 dB. Typically, you want to see greater than 27 dB for multimode applications. So the flat connectors are good enough for most applications, and the angle connectors offer even higher return loss. Next, we took those APC connectors and we unmated the interface that we were measuring the return loss at. So on the bottom right, we have the results from the unmated APC connectors. This is measuring the return loss of that angled glass-to-air interface. With a flat connector, we would expect around 14, 15 dB, but with these angled connectors, we see, again, over 45 dB of return loss. So even unmated APC connectors give you higher return loss than your mated UPC connectors. Next, we took those connectors and put them in several experimental setups to measure the impact of the flat and angled connectors on the actual system performance or on the BER itself. We had a commercially available 400G-SR8 transceiver that we tested, and it was driven by a 400G Ethernet tester. This tester generated the PRBSQ31 pattern and measured the BER, and we would average the BER over a 2-minute interval for all these measurements. Like I mentioned before, this SR8 transceiver had an angled interface, so it would accept an angled 16-fiber MPO connector. So we created a special fan-out cable. On one hand, it had a 16-fiber angled connector, and that was built with a single-mode ferrule. So again, a pre-angled single-mode ferrule populated with multimode fibers. And on the other end of the cable, we had a fan-out to 16 LC UPC connectors, so your typical flat LC connectors you see with multimode, and that was used to connect to the rest of the lab equipment. On the top left, I have our baseline or our back-to-back setup where we just took one lane at a time and connected it to a VOA, that's a variable optical attenuator, which was then connected to a switch. That switched between an optical power meter to allow me to monitor and receive power, or to one of the receive lanes on the transceiver so we could measure the BER. And we used the same receive lane on this transceiver for all of the measurements I'll show you today. After we did the baseline test, we took a series of APC multimode trunk cables. Again, these are cables that have multimode fiber but pre-angled single-mode ferrules in them. And we connected them so we had 6 of these angled MPO connections in the path between the transmitter and the VOA. We also had a pair of LCD MPO modules that happen to have flat connectors. After measuring the impact of the 6 APC connections, we removed those cables and replaced them with 6 12-fiber cables that had UPC, or traditional flat 12-fiber MPO connectors. Now, I had 2 sets of cables with flat connectors. The first one, we cleaned and inspected all the connectors very carefully. We also ensured that they were properly polished and that they had end-face geometry that was compliant to the standards. So that's our good set of flat connector cables. And then we had another set of 12-fiber UPC trunk cables that were problematic. They were clean but not inspected. Some of the end-face geometry was out of spec. Specifically, we had the problem with the X and Y angle. And after testing, we realized that one of these connectors had contamination on the ferrule that was causing an air gap. So we have a good set of flat connector cables and a set of problematic flat connector cables. And for the final test, we took those problematic cables and we put an isolator between the transmitter and those problematic cables to try to understand the mechanism or the impact they were having on the link. Here are the experimental results for lane 0. I'll report on 4 lanes that we tested today. On the left, we have BER versus received power for the controlled UPC. These are the good, clean, and well-polished connectors. The dark blue curve is the back-to-back. That's our baseline. That's when we had a minimal number of connections and fibers in the path. And we can see essentially no difference due to the well-controlled flat connectors. They have no penalty, no impact on the system performance. We see a little bit of a divergence at the low BERs, around 1E-10, 1E-11. I suspect that's due to the dispersion. We have about 12 meters extra fiber with the gray curve versus the blue curve from those trunk cables. So no penalty from the well-controlled flat connectors. If we look at the chart on the right, again, we have the dark blue curve is our back-to-back, our baseline. The orange curve is where we have 6 APC MPO connectors in the path, and we don't see a penalty with the APC connectors. So like the well-controlled UPC connectors, these angle connectors don't introduce a penalty. But if we look at the gray curve on the right, this is where we have the 6 flat connectors in the path, or connections, excuse me. But these are the problematic ones. There's some contamination, there's some poorly polished connectors, and we can see a penalty between the baseline case and when we have these poorly controlled connectors. So these connectors, they're problematic. The return loss isn't so high that it's causing the link to fail, but there's something else impacting the system performance. And if we look at the yellow curve on the right, this is the case where we have those same problematic connectors as in the gray curve, but we put an isolator between the transmitter and those problematic connectors, and that isolator mitigates or takes away that penalty from the problematic connectors. So this tells us that these problematic connectors are introducing a problem due to back reflection or poor return loss. If they were introducing a problem with modal noise or multipath interference or something of that nature, then the isolator wouldn't be able to mitigate those problems. Here are the results for lane 1. Similar to lane 0, the flat connectors don't introduce a penalty if they're well controlled, as we see on the left. On the right, when we have the angle connectors, again, they don't introduce a penalty, but those problematic flat connectors with the gray curve introduce a penalty. We see a linear offset at the higher BERs, especially near the FEC limit. And then we see a error floor around 5e minus 8, where we get to the point that the signal is so degraded that adding more power to the receiver doesn't improve the bit error ratio. So what we suspect is going on is these back reflections are making it back into the laser, which is increasing the noise of the laser. That intensity noise is going to degrade the BER for a PAM4 signal due to those 4 levels of modulation. Results for lane 2 are much the same. Again, no penalty for controlled flat connectors or for angled connectors. We have a problem with the problematic flat connectors that the isolator, again, mitigates and takes away any penalty that we see. And finally, we have lane 3, much the same as the other lanes, which is good news, helps us understand what's going on. So you can have flat connectors if they're well controlled. If you have contamination or poor polishing, that's introducing a penalty and actually degrading the system performance due to back reflection. The final experiments that I'll share with you is we took that lane 3 and we connected the transmitter from lane 3 to different ports on our LC to MPO module. So with these problematic 12-fiber flat connectors, the different paths or the different fibers on these 12-fiber connectors had different return loss values. So we looked at 5 different fiber paths on these cables, and we did 2 things. We measured the BER versus received power, as I showed you on the previous slides, but we also measured the cumulative return loss. So with our standard return loss equipment, we looked at the return loss of all 6 connections on these problematic cables for each fiber path and reported that here. So the light blue curve is our baseline. As before, this is where we don't have any problematic connectors in the path. If you look at the green line, that's fiber path number 5. It had a cumulative return loss of 11.4 dB. This is very close to the spec of 12 dB, which is allowed by the IEEE standard. And if we compare the light blue and the green, we see a slight penalty there. And if we look at the other curves, those return loss values are decreasing, which means worse return loss, or the problematic connectors are introducing, are having a bigger impact on the system. And we see that a good correlation as the return loss decreases, the BER does in fact increase. So the worse these connectors are contributing to return loss, then the worse the system performance that we're seeing. But again, as we get close to that 12 dB, we see that the penalty is very small, get close to the baseline case. So in conclusion, we demonstrated that the return loss of the connectors impacts the 400G-SR8 system performance, not just the loss, not just the return loss values, but the actual BER performance. Now, you can use your regular flat connectors if you can ensure that you have physical contact between the fibers, where you eliminate that air gap and make sure that when you mate the connectors together, that the fibers are actually touching. And you can ensure that you have physical contact from your flat connectors if you clean and inspect your connectors and ensure that they are properly polished so that their end face geometry is compliant to the standards. If you don't do those things and your UPC connectors have air gaps due to poor polishing or to contaminates on the ferrule, then that could introduce enough reflection that it increases the noise of the laser, and due to that extra sensitive PAM4 modulation format, you'll see a degradation in system performance. And there is an advantage to using APC connectors with this PAM4 modulation format because they offer a higher return loss even when they're unmated. So even if you have an air gap, the APC connector will ensure high return loss so you can mitigate the risk of this back reflection degrading your system performance. So thank you for your attention. I'm happy to answer any questions that you may have.
And thank you, Earl. At this time, we will take as many questions from the attendees as time permits, and we encourage attendees to submit their questions at present. Starting with the first question, you focused on the 16-fiber connector. However, what does this mean for existing 12-fiber MPO or LC solutions?
That is a great question. So far, I've only seen this come up with the 16-fiber connection or connectors, not with the 12-fiber MPOs or your regular LC connectors. So if you need, if you're asking, do you need angle with your 12-fiber or your LCs, it really comes down to a risk management question. If you can ensure you have good physical contact with your connectors, then you can use flat connectors. You don't need to switch everything in multimode to angle. And from my experience, it's easier to get that good physical contact the fewer fibers you have in the ferrule. So it's much easier to get good contact with LC connectors or 12-fiber MPO connectors than it is with the 16-fiber connectors. We haven't seen any angled 12-fiber MPOs or LC connectors for multimode. So I'm sure would be much more expensive than they need to be. So clean those LC connectors, clean those 12-fiber MPOs, and you should be okay.
Thank you. Next, Earl. Clearly sourcing of quality connectors assemblies matters. How does one check if air gaps are a problem in particular lots of connectors affecting performance?
Okay, there's two things that you can do. Measure the end face geometry. There's specifications for example, in IEC that say after you polish the connector, the angle it can have and the radius it can have. Those are designed to ensure that that physical contact. You can also measure the return loss. If you have a flat connector and there's an air gap, then the return loss will probably be 14 or 15 dB around there. If you have good physical contact, you should have 27 dB or higher. So that's something that I could do in my lab, for example. If an end user, that might be harder for them to do to measure the end face geometry, but definitely need to work with your suppliers, ensure that they're meeting the standards, and they can. Any supplier should be able to provide that data on end face geometry and return loss.
Okay, thank you. Next question. MPO assemblies are important for hyperscale data centers. Are data centers leading only to fiber, or are there still user applications for a copper link?
There are definitely applications for copper cables in hyperscale data centers. We're seeing over time those applications are for shorter and shorter reaches. So we're seeing the copper connecting shorter and shorter right now. I think it's more from like a top of rack switch to servers, but you're seeing multimode encroach more in that space as that becomes lower cost and more efficient. For example, there's a new study group in 802.3 that's investigating server to middle of row switch using multimode fiber applications.
Okay, thank you. Next, the focus here has been MM/APC at the transceiver. Can you comment on the need or value of the APC at the other end of the harness, the LC?
Okay, so that, again, depends on the physical contact. It's a lot easier to get that physical contact with your LC connectors, and that's why we're not seeing the angled connectors for multimode right now. getting 16 fibers to physically touch each connectors is trickier than when you just have one in LC or a duplex LC connector, getting both fibers to physically touch each other.
Okay, thank you. Next, is there a more sensitivity on the new PAM4 applications versus NRZ? Is that why we have not seen this before?
I suspect that's exactly why we haven't seen that before. So I didn't include an eye diagram in this presentation, but if you can imagine an NRZ eye diagram, you have two levels, a top and a bottom, and well, it's being equal for the same laser power. If you're, instead of using NRZ modulation, you're going to use PAM4 modulation, where you had two levels, now you have to squeeze in four. So those levels are a lot closer together. So any intensity noise, it's going to be felt a lot sooner with your PAM4 transmission than for NRZ.
Okay. At this point, I see no further questions, so we would like to thank you, Earl, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Earl after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, April 17th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 68 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader, showcasing new technologies in cable and connectivity products, processes, and applications. Our next 69th Annual International Conference will take place on Sunday, October 11th through Wednesday, October 14th, 2020, at the Rhode Island Convention Center in Providence, Rhode Island, USA. In addition, please note that our 2020 UL and IWCS China Conference scheduled for next week has unfortunately been canceled due to the coronavirus crisis. The next UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 23rd through Thursday, March 25th, 2021, at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.